All right, we're going to talk through our group work on 13.1 vector functions. Here we got a handful of different parametric equations for some curves, and we got to match them up with their graphs. And so we'll just kind of go at this with our different tools that we've figured out. So looking at this first set of parametric equations, just notice that it's for t greater than or equal to 0. Looking at the y-coordinate, that is just simply increasing linearly. X and z, however, are going to be wobbling just like cosine and sine do, but the factor in the front is going to end up scaling that. Right at 1, these will be scaling by 1. When t is 2, they'll be doubling cosine and sine. When t is 3, they'll be tripling them. And so x and z, I guess x to be careful, I guess it'll start at 0, and I won't be careful actually. I'm just going to draw the basic shape, something like that, right? And same with z is going to do something like that, wobbling more and more wildly as t moves out. And so looking for something like that, where notice y is only positive and x and z are kind of wobbling more and more. That looks like 2 here, where y is only positive for our curve, and we're moving out more and more wildly in the x and z directions. So A is matched with 2. Moving on to B, x and y are standard cosine and sine curves. So moving back and forth between -1 and 1. Also, if we wanted to, we could actually see that in the xy plane, right? Since we have this relationship that x squared plus y squared equals 1, we're actually moving around the unit circle in the xy plane. With the z direction, we have this rational function. And so as we plot that with respect to t, this is going to have a horizontal asymptote at 0, and at t equals 0, this will be 1 over 1. And so it'll start at 1 and then crunch on down to 0 on either side. And so we're looking for something where at different t values, x and y are just moving around the unit circle, and z is at most 1 and then kind of pulling down to 0 as t goes to infinity or minus infinity, which we are considering everything. So something like that, bounded z to start. Bounded z values could be 1 or 6. And only 6 seems to have this kind of spiraling around, kind of getting closer and closer and closer and closer to 0 for the z value. And so B is matched up with 6. Moving on to C, we see that, so for all t values, so x is just our standard line, slope 1. Y has this exact same look as we did before. Let me just piggyback on this graph. And then z is our favorite parabola. Next up, the origin there. All right, looking for something with bounded y values. X gets as negative as we want and as positive, and z never gets negative, so z is always positive. And in fact, we also have this relationship. If we look up, z is x squared. And so our curve lives on that surface. And so moving on over here, bounded y values could be this 3, could be 4, could be 5. Can't be 1 since x gets as negative as we would like. Similarly, it can't be 3. Looks like that is bounded for x values. I think if we use our imaginations here, we can imagine this curve here is going to be extending out that direction and this direction. So this is going to match up with 5. Notice also this curve only has the positive z values. All right, next. Moving on to D. And we have standard cosine and sine for our x and y coordinates. So we'll again have this relationship. As t increases, we're just going to be moving around the unit circle. Z, however, for this particular curve is also a cosine function, and so it's just going to be wobbling back and forth between -1 and 1. So z is bounded here as x and y move around the unit circle, and so it's like we've already done A, B, and C, these ones, and so looks like here this one it's moving around the unit circle, but z doesn't look to be moving back and forth. This one doesn't seem to be moving around the unit circle. This one, I think, if we imagine looking at it from above, could possibly be moving around the unit circle, whereas z is moving up and then down and then up and then down, and so it looks like D is matched up with 1. Moving on to E. Once again, x and y are some stretched cosine sine functions, but we're still going to have this relationship, actually, x squared plus y squared equals 1. So we're still moving around the unit circle in the xy direction. Z, for our particular function here, is an exponential. And notice we are only using t values at or past -2 pi. And so this exponential is going to look something like this. So there's our -2 pi t. So z is going to have some lowest value, and then it'll grow as much as we want from there. Again, this is as in the x and y direction. We're moving around the unit circle. And so if we look at our 6 possibilities over here, it looks like 4 is standing out. We're moving around the unit circle, right? Z starts off small, and then as we move around, z is getting bigger and bigger, and we'll keep on growing. So there's E. Last but not least, looks like F is going to match up with 3. One possible way we could see this is, actually notice x is already cosine squared, y is sine squared. So actually a relationship that we have, oops, too far, for these variables, for f is actually that x plus y equals 1, right? Because cosine squared plus sine squared equals 1. And so in the xy direction, it says y equals 1 minus x, so it's going to look like this. Our curve is just moving back and forth somewhere along this line, here, and z is just growing. It's our standard slope 1 line, and I will piggyback off of this graph for z. And so z is getting as negative as we want and as positive as we want, and x and y are kind of moving back and forth along this line. That looks like f, right? X and y are moving back and forth along this line, which in 3 dimensions, right, would extend in the z direction and give us a plane. and then z is moving down as far as we'd like, and then moving up as far as we'd like as well. All right, moving on down. Now we're sketching some curves using the vector functions, and we want to know what direction our vector function is moving as t increases. So looking at our vector function here, first thing I notice is that the z component is a constant. Right? If we want to write this in component form, it's t squared t2. So the z values on all the points this is tracing out are equal to 2. So z equals 2. And so in terms of getting a graph in 3 space, you know that every single point lives on the plane z equals 2. So we can trace that in, give ourselves some context. All right, what about x and y? What are those up to? Well, we can grab a quick relationship. Notice that x equals y squared. And so in the xy direction, right, this is a sideways parabola. And so that's going to look like over here in our picture. This is opening up in the x direction. It's going to look kind of like this, right, all inside the z equals 2 plane. And notice that when t is more negative, the y component is going to be negative. So at actually t equals y. So what we choose for t determines our y. So if t is like -2, well then we're gonna be down here on this curve. And as we increase t, our y coordinate is going to increase and give us this direction as t increases. So from negative y's to positive y's. So here on our graph, we move in this direction along this curve. All right, next one. Here we're seeing cosine and sine popping up. And so a quick relationship we can grab here is that y squared, plus z squared equals 1. And so in the yz direction, moving around the unit circle, and notice y is our cosine, z is our sine, and so here, y being our horizontal axis and z being our vertical, as t increases, we're going to be moving counterclockwise as we normally would around the unit circle, at least in the yz direction. Now, incorporating our x movement as well, here we see that x is equal to t. And so thinking about that, all right, this is our standard slope 1 function. So negative t's, we're going to get negative x's, and it's going to keep on growing. We can get as big as we'd like as we increase t. And so putting that together in 3 space, again, we're going to be moving in the xy direction around the unit circle for negative values of t. I'm sorry, I misspoke, didn't I? We're not moving around the xy directions unit circle. We're moving around the yz's unit circle. So here we go, something like that. And for negative t's, we're going to get negative x's. And then we're going to be spiraling around that unit circle, right, as we increase x. Maybe let's get a quick anchor point on here at t equals 0. What are we going to get? We're going to get 0, 1, 0. Let's maybe toss that on here. So 0 for x, 1 for y, and 0 for z. And as we increase, we're moving around the unit circle, increase in the x direction, something like this, always spiraling around that unit circle. And then similarly, I'll kind of rewind t back here to negative t, something like that. There we are. Yeah, and we want to show the direction that we move as t increases, and that is in the positive x direction. All right, last one. Here we have parametric equations, and notice they are all linear. So right away, we can tell that at least if we left t completely unbounded, these parametric equations would be tracing out a line. Here, since t is bounded between 0 and 1, it's going to give us a line segment. And so some different ways to think about this. If we'd like, we can just plug in 0, see what we get. T equals 0, we'll get x equals -1, y equals 2, z equals -2, and at t equals 1, we're going to get x equals -1, -2, so that's -3, y equals 2 plus 3, so 5, and z equals -2 plus 3, which is 1. So we'll draw this, and then I'll give us one more perspective on this curve. All right, so here we go. So we start at time 0 at the point -1, y is 2, z is -2, so down here. And as we crank t up, we're moving along the line, and we end up at the point x equals -3, y equals 5, and z equals 1. And I realize now that I have drawn this poorly. We'll fudge it. All right. So anyways, that's -1 for x, y is 2, z is -2. So x is -3, y is, let's say that's 5. And z is 1. And so here we start at this point at the bottom, and we're going to move along a line in that direction as we increase t from 0 to 1. I promised another perspective. Well, here if we'd like, we can actually take these parametric equations and reconstruct the point plus scaling a vector. This is going to be -1, 2, -2, looking at our constants, plus the scalings of our coefficients here on t, so -2, 3, 3. And so here we can see that this line kind of has its special point picked out as -1 to -2. And notice that's the point that we started at t equals 0. And then we're going to stretch up by scaling this vector. And at t equals 1, we'll have added one of those vectors. And actually, what we see here, if we added a little arrow tip there, that would be our vector -2, 3, 3. That lands us at this point that we get when t equals 1. All right, that's it for today. See you next time.